Yesterday, we introduced the idea of a vector. And today, we want to talk about operations that we can perform on vectors. We want to talk about how we represent the vectors, how to perform the operations, and how we can interpret what those operations mean. Recall that a vector is a quantity with magnitude and direction. A vector is a quantity with magnitude and direction. We're going to denote vectors with arrows. The magnitude of the vector will just be the length of the vector. So the other way we're going to read magnitude is as length. We're going to have notation to indicate the magnitude of a vector. And the notation is going to be like absolute value signs, but doubled up. We're going to double up our absolute value signs, and that's going to indicate the length of a vector or the magnitude of the vector. In general, the magnitude of a vector is a norm. And so the double absolute value signs is the symbol that we use to indicate the norm of something. In this case, it's going to be the norm of a vector. The norm of a vector is just its length. So that's the symbol for the length of a vector. Remember that the length of a vector doesn't have any direction, it's just a scalar. It's just magnitude. We're going to talk about how we picture vectors and how we write vectors. Then we can talk about the operations on them. So here's an example of a vector. It's 3i plus 4j. That means from the starting point of the vector, we go 3 in the horizontal and 4 in the vertical. Remember that I is just the vector 1, 0, and j is the vector 0, 1. I and j are the horizontal and vertical components of the vector. So 3i is the horizontal component, 4j is the vertical component. We haven't talked about operations on vectors. Part of the reason for that is it works exactly like you think it would work. If I take the vector 1, 0 and multiply it by 3, if you're guessing we should write 3, 0, you're correct. And if I want to multiply the vector 0, 1 by 4, you're guessing that's probably going to be 0, 4. You're correct. If you've seen this before, you would have known that. If you hadn't, you'd have guessed that anyway. Nothing fancy here. There's how we do scalar multiplication. There's our first operation on vector. Scalar multiplication. Take a vector, make it longer or shorter, maintain its direction. So here is the operation of scalar multiplication. I should say multiplication of a vector by a scalar, but that's a little bit too much to say, so I'm just going to say scalar multiplication. All we're doing is increasing or decreasing the magnitude of the vector or maintaining its direction. The vector 1, 0 goes horizontal. The vector 3, 0 also goes horizontal. We maintain direction. We change magnitude. So scalar multiplication will change magnitude. Maintain direction. In other words, we are scaling the vector up or down. That's all we call them, scalars. Now I'm looking at the vector 3, 0 and trying to add it to the vector 0, 4. You may have seen vector addition before, so you know how this works. But if you've never seen vectors being added before, it works exactly like you think it should work. We're going to add the corresponding components. And that's vector addition. We just add the corresponding components. Here we only have 2 because I'm about to draw this. But if we got 3 entries, we just add the corresponding components. If we have 4 entries, we just add the corresponding components. If they have a different number of entries, we don't get to add them. It doesn't make any sense to add them. It doesn't make any sense to add the vector 3, 0 to the vector 0, 4, 5. That doesn't make any sense at all. There's different things, you can't add them. That goes back to our first rule in math. We only add things that are the same, and when we add them, it doesn't change what they are. If I got $3 and I get $5, I have $8. If I start with $3 and I find 5 pencils, I don't have 8 of anything. We don't add things that are different. So here's the operation of vector addition. We just add the corresponding components. So here we see how scalar multiplication works. Here we see how vector addition works. When we're looking at vectors, this is the operation, these are the operations that we perform. Scalar multiplication takes a vector and stretches it, scales it up or down. So we started with the vector 1, 0, and we multiplied by 3. So if we start with the vector 1, 0, when we multiply by 3, we just keep the direction and make it longer. It's been scaled up. With vector addition, we just tack one vector onto the end of the other vector. Tack the beginning of the second vector onto the end of the first vector. So at the end of 3, 0, I'll put on 0, 1. And then we've also scaled this up by a factor of 4. So instead of just being 1 unit long, It's 4 units long. We take the end of one vector and track it to track the beginning of one vector to the end of the other. The thing that we do when when we add vectors is we're just adding the corresponding component. Geometrically, what we're doing is taking one vector and tacking it onto the other vector. The sum will go from the beginning of the first vector to the end of the second vector. So now we have two operations. We know how the operation works, what we do, how do we put the symbols around the page, and we can see how we visualize what's going on. Any questions? It's great in math when a thing works exactly how you guessed it would work. Like when you were learning derivatives and you had a function with two terms. You didn't have to be told that you take the derivative of each term. That's exactly what you would guess anyway. So it's kind of a shame if your instructions like all the derivatives with respect to x of f of x plus g of x is the derivative of f of x plus the derivative of g of x. Better to just say, here's a sum. How would you find the derivative? Because the thinking that you imply, that you employ, I wonder if this is a linear operator. And it is. It's a linear transformation. For those of y'all who've been through linear algebra. The questions on these first two operations. Notice that I could have started with the vector 0, 4 and put the vector 3, 0 onto the end of that one. And I would have had the same resultant vector. So if instead of going horizontal first with 3, 0 and then doing 0, 4, if I started with 0, 4 and then from the end of 0, 4 tacked on 3, 0, I'd have ended up at the same place. It's a good thing it works this way, because if I add 3, 0 plus 0, 4, we add the corresponding components. If I change the order that I'm adding them, that better not change the result. Otherwise, I shouldn't be calling this addition, because addition needs to be commutative. Multiplication, that doesn't have to be, but addition needs to be commutative. It works out in the numbers too. 3, 0 plus 0, 4, that's going to be the same as 0, 4 plus 3, 0. We're still going to get 3, 4. Any questions? The reason I point this out, even though you're all looking at me like, oh, dude, isn't that obvious? I'm like, oh, yeah, but that's why I'm pointing it out. This is something that we're calling addition. It had better be commutative. Otherwise, we're going to have problems. It doesn't matter if we write the first one and then put the second one at the end of that, or if we draw the second one first and put the first one at the end of the second one. 0, 4 plus 3, 0 is still equal to 3, 4. Addition is commutative. If we're going to be calling an operation addition, we want it to be commutative. questions? We did an example in 2 dimensions, but we could just as easily do an example in 3 dimensions. I would draw it in 2 dimensions, and we would just pretend that it's in 3 dimensions, because I would just move the plane of the paper to be in the plane of the sum of the 2 vectors. An important thing to note is that if you write down 2 vectors and they're not on the same line, you are establishing a plane. Note that if we put 2 vectors together that are not collinear, we are building a plane. Not a plane fly through the airplane. So for example, if this was a vector 3, 4, 7, then I would just angle my paper until it fits the plane defined by those 2 vectors. And note, 2 vectors not on the same line define a plane. Two vectors that are not going in the same direction define a plane. In this case, as long as you have 2 vectors that are not on the same line, it defines a plane, whether we are in 2 dimensions, 3 dimensions, or 20 dimensions. You've got 1 vector and another vector going in some other direction, you are defining a plane. For those of you who have been through linear algebra, we are talking about the span of that set of vectors. If you haven't been through linear algebra, we are still talking about the span of those set of vectors. You just might not have heard that terminology. Two operations that we can perform on vectors. Halfway there. We talk about how to perform the operation, and it's just how to put the symbols around the page, and how we visualize what's going on. So let's go down our list. We've got scalar multiplication. That's multiplication of a vector by a scalar. We've got vector addition. This is where we add 2 vectors. So if you're expecting something like a vector multiplication to come up next, you are correct. I'm going to be able to take vectors. How do we take a vector and multiply it by another vector? And there are 2 ways you can take a vector and multiply it by another vector. So we got to talk about vector multiplication. There are 2 things that can happen if we multiply a pair of vectors. I can multiply 2 vectors and come up with a scalar, or we can multiply 2 vectors and come up with a vector. So we've got 2 kinds of vector multiplication. There's a scalar product and a vector product. Each one will have a different operation. Each one will tell us a different thing about those vectors. So the first one is a scalar product. This is where we take a vector, multiply it by another vector, and come up with a scalar. So in a scalar product, it's vector times vector equals scalar. Note that when I said times here, I said vector dot vector. I put a dot in between and between the multiplication. And so the scalar product is often known as the dot product. So they use this symbol to represent the scalar product of a couple of vectors. So sometimes the scalar product is called the dot product. The other kind of multiplication that we have is a vector product. This is where we take a vector, multiply it by another vector, and come up with a vector. Thus, the product is a vector, so we'll call it the vector product. Aren't we clever in naming things? Actually, used to be way worse. We used to come up with weird names for things. But then we're like, oh, why don't we just call the things what they are? Like if I give you an ordered pair, one of the coordinates is called the ordinate, and the other one is called the abscissa. And I do not know which one is which. I've been doing math longer than most of you have been alive, and I don't think I've ever known if it's the ordinate and the abscissa or the abscissa and the ordinate. It's just not how we talk about math anymore. We just say x coordinate and y coordinate. But I don't know which one is which. You know what a subtraction problem? So A minus B equals C. We know that C is called the difference of A and B. But A and B have names too, because we used to name things. I think because we didn't have Xbox. Well, what are we going to do today? How about we name some math things? Awesome. Here are the terms in a subtraction. One of them is the minuend, and the other one is the subtrahend. Now you might be wondering which one is which. That's a good question. I don't know. Every time I look it up, that's the only moment that I know that information. As soon as I turn away and go do something else, gone. This is not just because I'm losing my memory. This has always been the case. I've probably known several times which one is the ordinate and which one is the abscissa, but it's never important enough for me to remember, so off it goes. In a vector product, we take a vector and we multiply by another vector and come up with a vector. You'll notice that very conspicuously, I use X to indicate the multiplication here. And that tells us what this product is called. This product is called the cross product. Each of these products has some kind of mechanical thing to do. How do we compute the product given a couple of vectors? How do we compute each of these products? And then we got to think about what it represents. When we calculate this product, what is that product telling us? And I guess there's the third thing. Why do we care? So for each of these operations, how do we perform the operation? And what does the product indicate? How do we perform the operation? And what does this product tell us? Once we have those two things down, we can ask questions, why do we care? I need to rephrase that question. I'm going to say, what do we do with this information rather than why do we care? There might be a perfectly valid thing for you to be like, oh, you know what? I don't. And then you pack your stuff and go. Which is an option. I'm not sure that many of you realize it yet. I haven't started in on trying to talk you out of going to college, but that's coming. I really, usually I don't try very hard in Cal 3, because in Cal 3, you're like, oh, dude, I'm this far. I'm just going to keep going. Even though you're not halfway yet. And in the case of you, you better understand how rounding works. I'm concerned because I realize that we've done a pretty good job of selling young people on the idea of going to college. Most of you are here because it's just the natural next step. That's what you do after high school, isn't it? I was like, oh, now after high school, plus after you turn 18 in this society, you do, what's it called? Whatever you want. You ain't got to do this. And this is the concern that I have. You may have been told, go to college, get a degree in STEM, then you'll get a job and be set for life. And I'm not sure that that's been true for 20 years, maybe 30. If y'all were my age and you were in high school and someone said, go to college, get a degree in the STEM field, then you'll be fine. You'll be able to find a job and you'll be gainfully employed for the rest of your life. It was true back then. The problem is, a bunch of us did that, and I'm not sure that it's true anymore. I guess my point is, if you're getting advice on how things work, like college and jobs and things like that, and the person is my age, don't listen. Don't listen to anybody that just says, go to college, then you'll get a job. I'm not sure that that's true anymore. You know what I mean? Especially if you don't do something while you're in college. People that are my age, all they had to do was go through college, get the certification at the end. They could still not really know how to do anything, and they'd be fine. They'd get hired somewhere. You know what I mean? It's like the early 90s. So people that are telling you that have been employed for a long time are giving you like 25 to 30-year-old advice that just might not be true anymore. So find people that are actually doing this, because I haven't applied for a job in over 20 years. So what the hell could I possibly know about applying for a job? You know what I mean? My concern is that you've been sold a bill of goods. And that's why I want to talk people out of going to college. Because if you're not committed to this, if this is not something that you feel internally that you have to do, not because some external force is trying to convince you that you have to do it. But if you're like, oh no, I'm here to learn stuff, then you have a chance of getting through it. If you're only doing this because your parents told you you had to, I promise you, you don't. It might result in some pretty crappy situations for y'all. I don't know, maybe your parents will kick you out of the house. If your parents have ever threatened to kick you out of your house, I really give them an F as a parent. You know what I mean? Do this because you have to do it, not because someone else said you have to do it. If you have no idea what you want to do, and you just want to try some stuff out, and this is not going to put you in a lifetime of debt, sure. Right? But if you don't have those advantages, then try to find something else if you're not properly motivated to do it. It's a huge investment of time and money. All that's to say, I needed to talk about nothing while the ink was drying so I could turn the page. That's just strategy right there. Let's talk about the dot product. Like I said, we got to talk about how to compute the dot product, and then what does the dot product tell us? So let's start with a couple of generic vectors. I'm going to pick generic vectors in R3, but the vectors can come from anywhere. Notice that V and U have little arrows on top. Those are vectors. Notice that V sub 1, 2, and 3 and U sub 1, 2, and 3 do not have arrows on top because those are scalars. The components of a vector are scalars. Two ways we can compute the dot product. One of them tells us what the dot product is telling us. So the dot product, V dot U, is V1 times U1 plus V2 U2 plus V3 U3. Notice that this is going to be a scalar. I just find the sum of the product of the corresponding components. The sum of the products of the corresponding components. Just a mechanical thing that we are working on. The sum of the products of the corresponding components. The products of corresponding components, these are scalar products because the components are all scalar. So it's implied that the product is just a scalar product. But the dot product is the sum of the products of the corresponding components. This is one way to calculate the dot product. The other way to calculate the dot product tells us why we might want to know the dot product. We could also calculate the dot product by taking the magnitude of V, multiplying by the magnitude of U, and then multiplying by the cosine of the angle between the vectors. Magnitude of V times the magnitude of U times the cosine of the angle between the vectors. The magnitude of a vector is just the length of the vector And we can calculate that using the distance formula. So the magnitude of V is just going to be the square root of V1 squared plus V2 squared plus V3 squared. The magnitude of U would be similar. Cosine of theta. Theta is the angle between the vectors U and V. Remember before what we said, it makes sense to talk about the angle between the vectors V and U, because if we draw two vectors that are not on the same line, then we are talking about a plane. So the angle is just the angle that we would find in the plane between those two vectors. The picture that we would be looking at, no matter what dimension these vectors are in, I have V going one direction, I'd have U going in some other direction. There's only two vectors here. So they are sitting in some plane, and theta is just the angle between the vectors. Already, this looks useful. This dot product, just looking at the components of a vector, of the vectors, we can figure out what the angle between the vectors is. Already, this is useful. I can just look at components, and rather than having to break out my 3D graphing and figure out the plane that they're in, figure out the angle between them, I just calculate the dot product and divide by the magnitude of each of the vectors, and that'll give us the cosine of the angle between the vectors. Already, just this definition of the dot product is useful information. Let's take a look at this cosine of theta business. If the vectors U and V are going in the same direction, then the cosine then the angle between them is going to be 0 degrees. If U and V are going in the same direction, if U and V are collinear, that is, they're going in the same direction, then the angle between the vectors is 0 degrees. And the cosine of 0 is equal to 1. So if U and V are going in the same direction, that means the dot product is at its highest value. If the biggest that cosine of theta can be is 1, cosine of theta will be between 1 and -1. That's the biggest value of cosine that we're going to get when cosine is 0, or cosine is 0. When theta is 0, cosine is 0. So that's like the biggest that u dot v can be. It's just the product of the magnitude. Now, as the angle increases, the cosine of the angle will decrease until the vectors u and v are perpendicular. At which point the angle between them is 90 degrees, and the cosine of 90 degrees is 0. So if u and v are perpendicular, if u and v are perpendicular, then the angle between u and v is 90 degrees. And so cosine of theta is equal to 0. So here's a way to find out if vectors are perpendicular. If the dot product of vectors is equal to 0, then the vectors are perpendicular. So we can turn this around. If u dot v is equal to 0, then u is perpendicular to v. That's bad grammar. You are perpendicular to v. Also note that after 90 degrees, cosine is going to come back negative. All the way down to -1. When we get the angle between u and v to be 180 degrees, the cosine of 180 degrees is -1. So the dot product will be at its negative maximum value. So that would be described u and v going in opposite directions. Any questions? So there's a dot product, how we calculate it, and what it tells us. Already, just by the definition, the dot product looks like it's going to be useful. It's telling us something about the angle between vectors. That's useful. This is related to the law of cosines being the generalized Pythagorean theorem. C squared is equal to a squared plus b squared in a right triangle. Because the term from the law of cosines minus 2ab cosine of theta, if theta is 90 degrees, because C is the hypotenuse, then that term is equal to 0. And you just get c squared is equal to a squared plus b squared. But in general, the generalized Pythagorean theorem is the law of cosine. C squared is equal to a squared plus b squared minus 2ab times the cosine of gamma, if gamma is the angle opposite side C. Any questions? Comments? Any thoughts? Of course, there's no questions. I've just gone into overtime. So that's going to do it for today. I will see you all on tomorrow when we'll talk about the cross product. Everybody have a good day, and thanks for playing.